Nuclear decay process and the energy of nuclear reactions are going to be the topics of this lesson in my new general physics playlist, which when complete will cover a full year of university algebra-based physics. In this lesson, we're going to take a look at the spontaneous processes of nuclear decay, and that's going to include alpha decay, beta decay, and gamma decay. And then we're going to move on to talking about the energy of nuclear reactions. We'll talk about their Q value, which can be used to see if they're either exothermic or endothermic. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. So we're going to start this lesson off talking about the spontaneous processes of nuclear decay, and it's going to include alpha decay, two different forms of beta decay, and then gamma decay. Now in alpha decay, it's also called alpha emission, so because that exactly describes what's going to happen. So typically in alpha decay, you're going to have a heavy nucleus emitting an alpha particle. And so what that's going to look like is on the product side of the reaction arrow is going to be an alpha particle. And don't forget that an alpha particle can also be written as a helium nucleus. So you could see it written either way, but it's going to show up on the product side. It's not a reactant, it's being produced in the reaction and emitted by this heavy nucleus. So if you recall, we said that for all the atomic number elements greater than 84, they are all radioactive. And a good chunk of them, when they decay, undergo alpha decay. So real likely for heavy nuclei. So what you might need to further know from this is just how to predict the products of alpha decay. Now we've kind of looked at some, really loosely, some different nuclear reactions, but what you need to know is that in a properly balanced nuclear reaction, the mass numbers and the atomic numbers all need to be balanced. Now we're going to find out that the mass is not balanced. If you were to take the mass to several decimal places, you'd see that the reactant, the total mass of the reactants and the total mass of the products would not be the same. But the mass number, rounded to the nearest whole number, will be the same, balanced on both sides of the reaction arrow. And so in this case, if I asked you to predict the product of the alpha emission of uranium-238. Now uranium-238, radium has atomic number 92, so whether that's given or not, you'd be able to look it up on the periodic table and find it. But if you want to find out the product of alpha emission, well then you should know that it's going to emit an alpha particle, 42, and then some other nucleus. And so what would be the product? Well, again, the mass numbers have to be balanced. So if uranium on the left side of the arrow here is 238, then 4 plus what here is going to equal 238, and that's 234. Same thing, the atomic numbers have got to be balanced on both sides of the arrow as well. So we've got a total of 92 on the left-hand side of the arrow. So far we've got 2 plus another 90 would give a total of 92. And then we'll look up atomic number 90 on the periodic table, and you'd see that that is the element thorium. And so this would be the product of alpha emission or alpha decay of uranium-238. And that's exactly the kind of question you might have to ask. And so if you notice, if you can write it out like this and just balance it out, life is good. But sometimes it's presented as just saying that the mass number is going to go down by 4 and the atomic number is going to go down by 2 when you undergo alpha decay. Now we're going to move on to talking about beta decay. And it turns out there's two different types of beta decay. And so sometimes you'll see it written as kind of beta minus and beta plus decay. And beta decay, so a beta particle, simply put, is an electron, sort of. It could also be a positron, it turns out. And the positron is just the antiparticle of an electron. It's an electron in all respects, except that instead of a negative charge, it has a positive charge. And that's a positron. And so we're going to see there's going to be both electron emission and positron emission, both kind of under this guise of beta decay. Now if we do electron emission for beta decay, or sometimes called beta minus decay, written in such fashion, so how would we predict the product? Well, again, so it's an emission, and when you have an emission, that thing is being produced and is therefore going to show up on the product side. And so in this case, we'd have a beta particle, which again also could be written as an electron, which has a mass number that rounds down to 0 for the nearest whole number, and then a -1 charge. So in fact, I'm going to get into a little trouble here, but again, you could write it as beta or electron. So with a positron emission instead, you're still going to produce a beta particle, but this time a positively charged beta particle, a positron instead, which once again could be written with the letter E for positron, positively charged electron in this case. So if I was going to ask you to predict the product of the electron emission or beta emission of a carbon-14 nucleus. So, well, then you'd set up your reaction once again. You'd produce that beta particle, -1, 0, plus our mystery particle. And once again, in any nuclear reaction, so the atomic numbers and the mass numbers have to be balanced. So in this case, 0 plus what equals 14? Well, I'm going to need another 14 for the mass number. So, and then -1 plus what equals a total of 6 on the left-hand side of the arrow, and that's going to have to be 7. And then we look up the periodic table, and again, it's always the atomic number, not the mass number, the atomic number that determines the element. So an atomic number 7 corresponds to nitrogen in this case. And so this would be the reaction, at least it would be most of the reaction. So it turns out that there's one extra little piece to beta decay that is not going to be included in how we balance this. It doesn't show up in the mass number, it doesn't show up in the atomic number, and it turns out it's what we call a neutrino. So, and if this neutrino didn't exist, it turns out that momentum would not be conserved with just the particles we have listed. And so it was predicted that this neutrino, this other particle, it wasn't called a neutrino yet, but this other particle should exist that somehow is going to account for it. And it turns out it's really difficult to detect, but it was later on detected. So it turns out there's both a neutrino and an antineutrino, kind of like there's an electron and a positron, which is the antiparticle of the electron. Well, the antineutrino is just the antiparticle of a neutrino. And they have a different form of charge called a lepton number, which is way beyond the scope of this course. But needless to say, so you probably should list it as part of the answer here. Now, it turns out it's the Greek letter nu, which kind of looks like a V, but it's the Greek letter nu. It's technically not a V at all. So if you put the bar over it, that represents an antineutrino. So and it turns out for electron emission, it's an antineutrino that's going to be used to balance the reaction. So, but for positron emission now, and so the question you got is, what is the product of the positron emission of potassium-40 here? Well, in this case then, your product, again it's an emission, would be a positron with a +1 charge instead of a -1 charge. And so if you want to know what your mystery nucleus is on the product side, well, 0 plus what equals 40? Well, 0 plus 40 equals 40. And then 1 plus what equals 19? And that's going to be 18. So, and if you look on the periodic table, atomic number 18 is indeed argon. And this thing looks balanced. But again, for electron emission and positron emission, you got to remember that for electron emission, you have an antineutrino also produced. And for positron emission, it's just plain neutrino, not an antineutrino that's produced. So, and again, I'm not going to provide any evidence of why one's a neutrino and antineutrino. Just take it for granted. So, but in any properly balanced electron emission or positron emission, you should include the antineutrino and the neutrino respectively. If you've seen this in a general chemistry context, we ignore that in general chemistry entirely. So, but again, from a nuclear physics perspective, momentum would not be conserved if those particles were not included. And so we do from that perspective. So if you have seen this in general chemistry, just know there's a slight revision that makes it more technically correct here. Now, one other thing you should note here about both electron emission and positron emission. So take a look here at what's really going on in going from carbon-14 to nitrogen-14. So your mass number is not changing, but notice your atomic number is going from 6 to 7. So if we take a look here, so at carbon, carbon's got 6 protons, so, and then 8 neutrons. But nitrogen here has got 7 protons, the atomic number is the protons, and then the difference again between the mass number and the atomic number is the neutrons, so 7 neutrons. And so if you notice, we go from 6 protons to 7 protons, we gain a proton. But we go from 8 neutrons down to 7 neutrons, we lose a neutron. And the reason here is because ultimately we're actually converting a neutron into a proton. So if you look, you can kind of think of having a neutron as kind of the combination of a proton and an electron combined. So if you took a proton +1 charge, a mass of roughly 1 unified mass unit, and you combined it with an electron with a -1 charge and a mass number of 0, but a very small mass, you would form something that now has a 0 overall charge, +1 from the proton, -1 from the electron, and still a mass number that's effectively still 1, because the electron is such a small fraction of a mass of a unified mass unit. And what has an overall charge of 0 and a mass number of 1? Well, that's what a neutron has. So, and in this case, if you take that neutron then and split it apart into a proton and an electron and eject that electron out of the nucleus, that's what we're doing in electron emission. We're ejecting the electron that was produced out of the nucleus, leaving a proton behind. And so you should also know that for electron emission here, so you have the net conversion of a neutron to a proton. Now we're going to see the exact opposite for positron emission here, where it's going to convert a proton into a neutron. So if we look at potassium-40 first, it's got 19 protons and then 21 is the difference, neutrons. So whereas argon-40 has got 18 protons and then 22 neutrons. And so if you look, we're decreasing the number of protons by 1, but increasing the number of neutrons by 1 instead. And so ultimately, this is the net conversion of a proton to a neutron. And so in this case, by ejecting out a positron, what you're effectively doing is getting rid of the positiveness of a proton. And if you get rid of the positiveness of a proton in some way, shape, or form, what's left behind is something that still has a mass number of 1, but now a charge of 0, which is indeed the neutron. So you should also know that electron emission is the net conversion of a neutron to a proton, and positron emission is the net conversion of a proton into a neutron, just the exact opposite. And once again, you should be able to predict products, so of either electron emission or positron emission. All right, finally, the last one we'll talk about here is gamma decay. So in gamma decay is probably the easiest of these. So with gamma decay, it's also called gamma emission. So, and you're going to produce not a particle, but a gamma, that's a terrible looking gamma, but a gamma ray. And a gamma ray is not a particle. It's actually super high energy electromagnetic radiation. So it's really high energy light, higher than X-rays, higher than ultraviolet, way higher than the visible spectrum. It's the highest region we kind of define on that electromagnetic spectrum. So super high energy light. Now it turns out that gamma decay usually doesn't happen on its own. It usually follows one of these other spontaneous decay processes. So it turns out, just like with electrons, so electrons can absorb energy, and like we saw with the Bohr model of the atom, they can jump to higher orbits. Well, it turns out they're just really jumping to higher energy orbitals, but when they relax back down, they actually emit a photon of light instead. And sometimes those will show up in the visible spectrum, sometimes in the infrared, sometimes in the ultraviolet. It really depends on which energy levels, i.e. which orbitals we're jumping around from. Well, it turns out that nuclei also have excited states. They have higher energy levels. And so after doing alpha decay or beta decay, a nucleus is often found not in its lowest energy state, what we might call the ground state, but in some sort of excited state, some higher energy state. So, and in dropping down, it turns out that the gap in energy is actually really huge compared to the gaps we saw for electrons in the orbitals. And so when it drops down to the ground state, the energy it gives off is much larger in energy than, say, the visible light or the ultraviolet light or the infrared light we might have seen for electrons. And so in this case, it corresponds to a gamma ray. But keep in mind, this really is just a ray, not a particle. It's part of the electromagnetic spectrum. And so it actually doesn't change the identity of the nucleus at all. It just lowers its energy state. And so in this case, if you wrote the products here, so of gamma decay for cobalt-60, it's the easiest one to predict because it's still going to be cobalt-60. So because if we balance this with 0 and 0, and these are, it's not just a mass number that's rounded down to 0. Again, light really has a rest mass of 0. And so in this case then, I need 60 plus 0 equals 60, and then 27 plus 0 equals 27, and atomic number 27 is still cobalt. So, and there you go. Sometimes you'll see, some people will put like an asterisk right here to show that it was in an excited state. Sometimes you'll see it, sometimes you don't. It's not necessary. So, but the key is we're just going from some form of high energy excited state down to some lower energy ground state. And gamma emission typically follows some other nuclear decay process. Usually doesn't happen all by itself. Now we're going to take a brief look at the energy of nuclear reactions. And if you kind of compare a nuclear reaction to a chemical reaction, so there's one key difference. In a chemical reaction, you have all the same atoms. They might be bonded in different ways, and that's how you account for kind of the difference in energy, is the difference in the energy of the bonds of the reactants versus the bonds of the products. But all the atoms are still there. And so the total mass of the reactants and the total mass of the products is exactly the same, and mass is conserved in a chemical reaction. But in a nuclear reaction, that is never true. If you take, for instance, nuclear fission or fusion, both of which produce massive amounts of energy. Nuclear fission, this is what happens at our nuclear reactors. Nuclear fusion, this happens at the center of the sun. Both are highly exothermic. And the reason they produce so much energy is that we're actually converting mass into energy in both nuclear fission and fusion. And when you convert mass into energy, this is the equation we use to figure out how much energy equivalent it's being converted into, E equals mc squared. And a little bit of mass timed by the big fat speed of light squared turns into a lot of energy. So, and it turns out it's not a lot of mass that's being converted to energy, per reaction, if you will. So, but it doesn't have to be a lot because a little bit of mass turns into a lot of energy. So that's one key difference with nuclear reactions. So is that mass is not conserved. Now, if you look, you might be, we're actually going to calculate the difference in mass in this reaction right here. And you might look and be like, wait a minute, Chad, it kind of looks like it is conserved because 16 plus 1 is equal to 4 plus 13. You told me that when we balance these, you balance the mass numbers. That is true. I told you we balanced the mass numbers. But don't forget that these mass numbers are just rounded to the nearest whole number. But if we look at the exact masses to several decimal places, that's how far you have to go to figure out this difference in mass between the reactants and products in a nuclear reaction. It's usually some small fraction of a unified mass unit. So just word the wise. You might be like, looks like mass is conserved, until you look really closely and realize that mass is not conserved. Now it turns out we describe this difference in mass and its energy equivalent as the Q value of a reaction. Now for something like nuclear fission and fusion, which produce lots and lots of energy, they're exothermic. And being exothermic, we define them as having a positive Q value. But there are nuclear reactions that are endothermic. They're going to require the input of energy. And we'll define them as having a negative Q value instead. All right, so if we look at nuclear fission and fusion again, you're always converting mass into energy in those two processes. And so your products will always weigh less than your reactants. And when that's the case, that's when you get a positive Q value. But if your products weigh more than your reactants, that's an endothermic process. We're going to be converting energy into mass along the way. And so we're going to be losing some energy along the way, consuming some energy along the way. And for that endothermic process, Q would end up being a negative number instead. Now, one thing that's going to make this a little bit of a pain in the butt. Oftentimes, we're going to give you the masses of nuclei and the relevant particles in unified mass units. And when you find this difference in mass, you'll plug it into E equals mc squared, but you'll have to do a conversion first. So typically you need to use some SI units here, and for mass, that's kilograms. And to convert a unified mass unit into kilograms, this is your conversion factor right here. So you convert your unified mass units into kilograms first, multiply by the speed of light in meters per second, and then square it. And you get an energy, which will also come out in SI units of joules. The problem is when we're dealing with really small things, and we saw this with electrons earlier, but when you're dealing with really small things like individual nuclei and nuclear particles and stuff like this, it's often more convenient, instead of dealing with joules, to deal with either electron volts, or as we'll see in this case, mega electron volts. You might recall that 1 electron volt is 1.6 times 10 to the minus 19 joules. So you're going to convert the difference in mass, which is in unified mass units, to kilograms, so that you can plug it in here and get an energy in joules, which you can then convert to electron volts and then eventually to mega electron volts. Yes, and it's a huge pain in the butt. Or somebody was nice enough to see that with nuclear physics, we do this so routinely that they give us a lovely conversion factor that 1 unified mass unit is the equivalent of 931.494 mega electron volts per the speed of light squared. This is a unit of mass. And when you plug this unit of mass into this formula and multiply by c squared, that c squared cancels that c squared, and you get an energy right off the bat in mega electron volts. And so if you calculate your difference in mass in unified mass units and then use this conversion to convert it into mega electron volts per c squared, well then your Q value would be that same number of just simply mega electron volts, kind of after you multiplied by c squared in that equation. So a much easier way to go in the route we're going to go. All right, so let's take a look at this then and figure out our Q value for this reaction. So we're going to sum up the masses of the reactants and products. We'll let our calculator do the heavy lifting. So 15.99491 plus 1.00728 is going to get us 17.00219 unified mass units. And on the other side, we've got 4.00151 plus 13.00574. We're going to get 17.00725. Unified mass units. And so if we calculate delta M here, and truth be told, I'm just going to calculate the absolute value of this difference in mass. But if you notice, they're both 17 here, but 0.002 versus 0.007. And so in this case, the products actually weigh a little bit more than the reactants. And so over the course of the reaction, we'll have had to convert energy into mass. This reaction is going to consume energy. It's endothermic, and it's going to have a negative Q value in this case. So if we take 17.00725 minus 17.00219, we're going to get 0.00506. So again, that's in unified mass units. And then we'll just use this conversion factor right here to convert it to mega electron volts per speed of light squared. And so in this case, we're going to have 1 U on the bottom, and then 931.494 mega electron volts per C squared. And so we'll take our 0.00506 times 931.494 and to several decimal places here, get 4.71336. And that's in mega electron volts per C squared. Well, again, if I want my Q value now, so my Q value would come if I plugged this difference in mass right back into this formula multiplied by C squared, which simply just cancels out that right there. And we get a Q value, at least the absolute value of which would be 4.713, I lost a 3 there, 36 mega electron volts. But keep in mind, this is an endothermic reaction, which we define as having a negative Q value. Much faster route of calculating it than, turning our unified mass units into kilograms, getting joules, converting joules to electron volts, and then to mega electron volts. And it's pretty common to report these Q values in mega electron volts, making that last conversion so convenient. So we got to ask ourselves a question then. So this reaction is happening at an energy deficit, and this is the energy deficit here, this negative 4.71336 mega electron volts. So how do we supply this reaction energy? Well, we do this in these are typically happening as what we call a nuclear bombardment, and we use a particle accelerator, which can accelerate charged particles to ridiculously fast speeds. And we're going to take this small particle right here, the proton, which is indeed charged, and we're going to speed it up in this particle accelerator really, really fast. Now you might be like, well, how much kinetic energy do we have to give it? Well, we have to give it enough kinetic energy that we're not operating at an energy deficit anymore. We might be like, well, then you have to give it 4.71336 mega electron volts. And you're close. And that's not a bad assumption, but it's off by one thing. So if we did give this proton exactly that amount of kinetic energy, because the Q value doesn't account for the fact that you might have some kinetic energy supplied to your reactants and stuff like that. But if you did give it that exact amount of kinetic energy, what you'd find then, though, overall, the energy of the reaction would now be 0. The Q value hasn't changed or anything, but the overall energy of the reaction is going to be 0, which means that there's no extra kinetic energy for the products. And that's a problem, because you had kinetic energy for the reactants, so you end up with no kinetic energy for the products, but the overall energy is balanced. So it's from an overall energy perspective, that's not a problem. From a momentum perspective, that's a problem, because this guy has momentum, he's got velocity. These guys, because they have no kinetic energy, means they have no velocity and no momentum. And if this is the amount of energy we give that lovely proton, momentum's not going to be conserved. And so it turns out, just simply looking at your Q value, and if it's negative, saying, well, that's the kinetic energy I have to give my reactant particle, that's not going to be enough. So it turns out we're going to have to give it a little more. That way momentum can also be conserved. And it turns out we got a nice lovely formula for the minimum amount of kinetic energy it needs to have, and it's this guy. And so instead of this value, we've got to multiply our Q value by some factor that factors in the mass of our nuclei that we're speeding up, and then the target we're ramming it into, this guy right here. So, and then multiplied by our Q value, or at least the absolute value of our Q value, and that's the minimum kinetic energy, and that's the last calculation we're going to do here. So, and our proton again weighs 1.00728 unified mass units. Our target molecule here that we're ramming it into is 15.99491 unified mass units. And as long as these have the same units, those units are going to cancel. So I'm just going to leave it in unified mass units. And then we'll multiply it by the absolute value of 4.71336 mega electron volts and get an answer here. And so if you notice, this number here is going to come out just a little bit higher than 1, making our minimum kinetic energy just a little bit bigger than our Q value. And so in this case, if I put in parentheses 1 plus 1.00728 divided by 15.99491, and my parentheses times, the last answer in my calculator is that one. Now we get 5.0102, so I'll round it to. Mega electron volts. And notice that is indeed just a little bit bigger than the 4.7 we might have thought would be the right answer. The 4.7 mega electron volts was the right answer without factoring in we need momentum to be conserved. And that is all there is to it. If you have found this lesson helpful, consider giving it a like. Happy studying.